Hello and welcome to our discussion on concepts of probability. This is a big topic, so we'll be breaking it down into smaller parts. First of all, we'll be looking at testing hypotheses. Next, we will be looking at the assumptions that are required in order to test those hypotheses. And then we'll be looking at level of significance. After that, we will run through two actual statistical analyses, and then finally we'll take a look at decision errors and statistical power. Now before we get started with that, I'd like to quickly review what we learned about populations and samples. When we have a population, usually we do not have enough resources to be able to measure everyone in the population. So instead, we take a sample, and of that sample, then we do this measuring. We measure whatever variables we're interested in, and then based on what we measured, then we go ahead and infer back to the population, and this inferring has everything to do with the hypotheses. So also as a quick review, here we have our population distribution, our sampling distribution of the mean, and then the sample distribution itself. And so if we were to have perfect knowledge of our whole entire population, then we would know exactly what its shape was. We do know that its location is the mean, and we could put that here. Our population average is the mean, and the spread is sigma. We'll put that here too. So population parameters are mean and standard deviation. For the sample that we did take, then the shape of our sample mimics that of the population, given that it's large enough. The location is x bar, and I'll put that here, and the spread is the standard deviation. And so we know a few things about the sample distribution and the population distribution and how those are related. Here, I'll put standard deviation over here too. And then based on the sample size that we take, we will also have a sampling distribution of the means of that population. This is all hypothetical, and that's why on this graph you'll see those as dashed lines. The shape of that sampling distribution of the means is normally distributed as long as it's a big enough sample size. Remember the central limit theorem. As long as we have a sample of maybe 30 or more. Some people say 40, but roughly 30 to 40 or more. The location for the sampling distribution of the mean is also mu, so it mirrors the location for the population distribution. However, the spread is equal to the standard error, which is equal to the population standard deviation, sigma, divided by the square root of n. So let's do an actual example based on this information. Let's say that we have a sample that we have drawn from our current population, and we know that the location for that, the average is 185, and the standard deviation is equal to, let's see, I wrote down on my notes, standard deviation is equal to 40. Let's say then also that we want to compare that to a historical sample, and let's say the mean for our historical sample used to be 170. And so we want to know now, in 2016, are people heavier than they used to be? The spread of that historical population was 40. So it looks like we have the same kind of spread that we used to. And the shape of the population distribution would be very similar then to the sample distribution. So for now, let's just assume that those are both normally distributed. Now, our sample size is n equal to 64 for this particular example. And so the main thing that we need to calculate right now is the standard error. So standard error is equal to sigma, which is 40, divided by the square root of 64, which is equal to 40 over 8, which is equal to 5. So that gives us all of the parameters we need in order to graph this particular example. So here we have the sampling distribution of the mean, and we know that the middle of that is going to be the population mean. One standard deviation to the left will be minus one standard error, and two standard deviations to the left will be minus 2 standard errors. Plus 1 to the right is equal to standard error, and plus 2 to the right is plus 2 standard errors. And I'm trying to draw this to scale for the sampling distribution of the mean. In other words, what we believe about this distribution here is that 95% of the standard, of the x bars, if we were to do this sampling distribution of the sample means, 95% would fall between plus and minus 2 standard errors. Now, if you recall, those correlate with an actual z-value, and the z-value for the mean is equal to 0. The z-value for plus 1 standard error is plus 1, and the z-value for plus 2 standard errors is plus 2. Similarly, we have minus 1 and minus 2 here. So 95% of our sampling means are going to be between plus 2 and minus 2 of a z-value. Now, if we actually put in the values that we have for our particular example, what we know is that our mean that we're testing is 170. Plus 1, I'm not going to write it on here because I want to leave it empty. 170 plus 1 standard error is equal to 175, and 170 plus 2 standard errors is equal to 180. Minus 2 standard errors is equal to 160. So we know that 95% of the time, if we were to draw from this population, this hypothetical population distribution with a mean of 170 and a standard deviation of 40, if we were to just draw samples of 64 over and over and over and over again, that 95% of those x bars would be between 160 and 180. So 95% would be here. Now, 2.5% would be above 180. So it's not totally unheard of. And another 2.5% would be below 160, if in fact it is normally distributed and has those same qualities. So that's just kind of laying out the question that we actually have. I'm going to do one more thing. I'm going to draw this x bar right here of 185 right here at 185. So I'll put the x bar at 185. So we can kind of see that visually. Now, let's go back and think about this whole idea of testing hypotheses, because in reality, what we know when we actually take this sample is we know what's in the sample. We do not know the population. We have hypothesized a population, and based on our hypothetical population and our actual sample size, we also hypothesize this sampling distribution of the mean. But we don't have a population that we did that to. Remember how we said we don't actually do this? So what we're doing is we're taking what we do know and we're writing a null and alternate hypothesis from those for this particular example. And the null hypothesis is that this sample that we drew, this sample, is likely to have come from a population with a mean of 170. And the alternate then is that this sample is not likely to have come from a population with a mean of 170. And so the important thing to remember about these null and alternate hypotheses is that they need to be mutually exclusive. In other words, they cannot overlap. And they also need to include all possibilities. And so the way I'm going to write this and show you these is I'm going to write these as h sub 0. This should actually be a sub-zero, but I can't make my font do that apparently on this computer program. H sub 0, mu is equal to 170. H sub a, or alternate, mu is not equal to 170. So what I've done here is called a two-tailed test, where I'm going to test whether the average is equal to 170 or if it's not. And if it's not, in this particular case, what that means is that it could be higher or it could be lower. And so it's actually the amount, it's the absolute value of the amount that's away from this middle point of 170. So when we are doing this particular hypothesis test, either that mu is equal to 170 or mu is not equal to 170, what we are testing then is that if the null hypothesis is true, then this set of information would be correct. If the null hypothesis, mu equals 170, is true, then our sampling distribution would be located here, our z-value would be located here, our 95% of the x's would be between 160 and 180. So that's what we're actually testing. So what we know is the sampling distribution, and that's it. We don't know the population distribution because we didn't measure everybody in the population. So just kind of keep that in mind as we go through this example. So that concludes this first video. Then we'll make another video for the next topic.